Hello everyone. The topic of this pre-lecture is momentum in quantum mechanics. Before I get rolling with that, I want to do a little bit of calculus review. I'm going to use something over and over in this pre-lecture, and I want to make sure we understand it first so I don't have to explain it each time. So just very simple. Suppose you have two functions, f of x and g prime of x. So prime denotes derivative with respect to x. If I look instead at f of x times g prime, according to the product rule, this is f prime g plus f g prime, right? So if I have f g prime up at the top, which is here, I can move this to the other side, and I can write it as f g whole thing prime minus the derivative on the other function f prime g. One of the reasons it's important, of course, is if this lies under an integral, suppose you have a to b f g prime dx, that would be the integral of from a to b f g prime dx minus the integral from a to b f prime g dx. This is the integral of a derivative. You know, the prime means derivative with respect to x, so this thing here just becomes f times g evaluated at a and b. This is integration by parts, of course, and one way you can remember it is, suppose I have something like this, f g prime. What I can do is I can switch the derivative to go on to the other function that's here, so now it's f prime g. I pick up a minus sign in front, and I pick up this term. All right, so we'll use this a couple times throughout this lecture where I have something like this. I switch the derivative to the other one, pick up a minus sign, and I have this other term to deal with. With that out of the way, let's start talking about momentum in quantum mechanics. We've learned that the wave function squared, psi star times psi, is a probability density. I can use that to calculate probabilities. I can also use it to calculate averages. For example, the average position x is the integral of psi squared times x, the thing I'm trying to average. It's common to write this in this form. So psi squared is psi star times psi, and I sandwich the x in between. It's common to write it like that, and we'll see why by the end of this lecture. Another quantity that we're very interested in quantum mechanics is momentum. So you might be interested in knowing what is the momentum, the average momentum of a particle, a quantum particle, if I know its wave function. And that's the goal of this lecture, is to write that in a fairly simple form. So classical physics, P is equal to mv, and v is dx dt, right? This is true in classical physics. In quantum physics, you can still use these same classical laws, but they only apply to averages. So what I would write here is the average momentum is the derivative of the average position with respect to time. So that's a general rule. If I have some classical equation, which I know from earlier courses, I can use that equation in quantum mechanics, but it only applies to averages. Average momentum is m dx dt, or putting it another way, it only applies to expectation values. And that's a special case of something called Ehrenfest's theorem. Expectation values obey classical laws. Okay, so I want this average momentum. I have the average position up there. I just have to take the derivative with respect to time and multiply by m. So here we go. I'm not going to write the x and the t arguments just to save myself some writing here. So you just have to remember that that psi is a function of x and t. The integral is over x. This is a derivative with respect to t. And by the way, x itself does not depend on time. X is a different variable than time. So let me bring this dt inside of the integral. And then let's use the product rule here. Okay, so far so good. This is my expression for the average momentum. I'm going to keep this equation separate, so let me clean this up a little bit, and then we'll do some more manipulation of this equation. Okay, so there it is. The rest of the lecture is basically manipulating this into a simple form. One thing that's annoying about this is the integral is over x, but the derivatives are with respect to time. We can make this simpler if we can switch these time derivatives for something else, and we can do that using the Schrodinger equation. just to be clear here, the prime means d by dx. Okay, so there's two derivatives floating around, one with respect to time, one with respect to x. The prime means derivative with respect to x. Okay, what I have here is d psi dt multiplied by psi star. So what I'm going to do is, let's divide the I h bar, okay? And then just to make it look like the thing over here, let me multiply by psi star. So let me multiply both sides by psi star. So psi star goes here, psi star goes here, and psi star goes there. Right? So this term here is exactly the same as this whole thing. Now what about this term? That term, if you think about it, is just the complex conjugate of this term, right? If I take the complex conjugate of psi star, I end up with psi. And if I take the complex conjugate of d psi dt, I end up with d psi star dt. So let me write this again, but take the complex conjugate of both sides. So this will be psi, d psi star dt, minus h bar over 2mi, but the I becomes a minus I when I take the complex conjugate, so that becomes plus. And then instead of psi double prime, I have psi star. And then instead of psi star, I have psi. And this term becomes minus v over I h bar, psi star times psi. This minus sign came because I changed the I to minus I. So what I did here to go from this line to this line is I took the complex conjugate. I took the complex conjugate of both sides. So this now is exactly the same as this term here. Let's add those two together because that's what we have in the integral. Okay, these two terms, I've got h bar over 2mi times, psi double prime star psi. And then I've got the same thing again with a minus sign, but now it's psi double prime psi star. And these two terms cancel, right? If I add this to this, so this cancels with that. So adding those two equations together, I get this. So this is another way of cleaning this up. So let me replace this with our new equation here and clean up the rest of the blackboard. Okay, so I've replaced it with that, and by the way, you can see that there was an m on the top and an m on the bottom, and so those cancel out. So you're like, what is the point of this? The reason this is useful is that this is an integral over x, and these are now derivatives with respect to x, and I can simplify this a little bit. Now let's take a look at, say, this term here. So what is that? That's psi double prime, psi star. This should remind you of the g prime times f that we talked about at the beginning. So it's some function times the derivative of some other function. We learned that this can be written as fg prime minus the derivative acting on the other function, so gf prime, right? So in this case, g is psi prime, f is psi star. So what I'm going to have here is psi prime, psi star, whole thing prime, minus the derivative acting on the other function, so it's psi prime, psi star, prime. That was this term here. Now the first term is the same one, but the complex conjugate of that, so let's write this complex conjugated. So I just took the complex conjugate of the line above it. CC is complex conjugate. The integral is the subtraction of these two. So if I subtract those two equations, what do I have? And when I subtract these two, I notice that these two are the same. So this cancels with that. And I'm left with the total derivatives, d by dx of psi prime, psi star, minus psi star prime. What shows up in these brackets is exactly this, but in the opposite order with a minus sign. So let me use this and plug it into here to simplify our expression. We are getting there slowly but surely. Okay, here we go again with the integration by parts. This is like f and this is like g prime, right? This is the f, and this is the g prime. So we learned how to do this in the beginning of the lecture. What do I get? I switch the derivative to the other term, I pick up a minus sign, and then I pick up the f times g term using the integration by parts. So let's do this by parts now. So my average p is going to be h bar over 2I. Okay, I have the term which looks like fg evaluated at the limits. So I have here x psi star prime times psi minus psi prime psi star evaluated at minus infinity, infinity. So that's the boundary term. And then I have the term where the derivative is on the other function, but with a minus sign. So I get minus integral minus infinity to infinity d by dx of x. So the derivative acts on x, and then this is the g term. All right. This term, when I evaluated at infinity and minus infinity, you remember that the wave function has to be normalized. So the wave function has to go to 0 at when x goes to plus or minus infinity. If it didn't, the area underneath could not be 1. So I have to have my wave function go to 0 at very large x. And so this will be 0 since psi goes to 0 as x goes to plus or minus infinity. Okay, so basically the fact that psi goes to 0 will kill this term. So this boundary term is all gone, including this. What I'm left with is this. The derivative of x is just equal to 1, and I have psi star prime psi minus psi prime psi star dx. Okay, I'm going to do that trick one more time on this term. So I'm going to do integration by parts on this. What will happen? The derivative will act on this, so I'll get an extra minus sign there. There will be a boundary term which looks like psi times psi star evaluated at minus infinity to infinity. But that boundary term will be 0 for the same reason. Let me do this first term just like we talked about. So it'll be psi star times psi evaluated at minus infinity to infinity. And then I've got the term in the other, or where the derivative is acting on the other function, psi dx. And then this term I still have, so this term I didn't touch. Okay, this term goes to 0 again for the same reason as up here, goes to 0. Psi goes to 0 as x goes to plus or minus infinity. And these two terms are the same. Psi prime psi star dx, psi prime psi star dx. So the last simplification was h bar over 2I. And then there were two terms which looked exactly the same, minus infinity to infinity. And it was psi star psi prime dx. Right? And of course the 2's cancel. Okay, so let's just clean it up a little bit. Average p. 1 over I is minus I. So minus I h bar, integral minus infinity to infinity. And I'm just going to write this in a little more explicit notation. D by dx, psi dx. And it's common to write this with the IH bar brought inside here. What I want you to do is compare this with the average x, which we had before, minus infinity to infinity, psi star, x, psi dx. So compare these two. To find the average position in between psi star and psi, I sandwich x, and then I do an integral from minus infinity to infinity. If I want to find the average momentum in between psi star and psi, I sandwich something, but it's not p, it's this weird thing, which is minus I h bar d by dx, meaning take the derivative of psi. This is called p hat, momentum operator. And then you can kind of see why, because now there's some symmetry between those two formulas. This is going to be a general rule. If I want to average something, in between psi star and psi, I put this thing which is called the operator, which corresponds to this, this thing I'm trying to average. So for x, the thing that goes in between is just straight up x. But for momentum, the thing that goes in between is not just p, but this operator p hat, which is minus I h bar d by dx. So this is very important, called the momentum operator, minus I h bar derivative with respect to x. So we've talked about how to calculate the average momentum. We have a prescription here, and we've identified this thing called the momentum operator. Thank you all for your attention. If you found this content helpful, please like and subscribe. Thank you.